Well, today's topic is force. We're going to do a little review. The first thing we're going to review is speed. We started out talking about displacement and speed and how they're related to each other. And what we saw when we did that was if you have a graph where you're graphing time and you're graphing displacement, no matter what the shape of that graph is, the slope at any moment there, like right at this point, let's say, the slope of the tangent that goes through there, well, that's equal to the speed. If you're at constant speed, something like this, well, that slope never changes. But if you have variable speed, you can have an instantaneous speed at a point, or you could pick any 2 points on the graph, draw a line through those 2 points, and the slope of that is your speed. Speed we often abbreviate with v, which is short for velocity, which we've seen is related to speed. So in terms of an algebraic symbolic equation, we can say speed or velocity, if you have a vector attached to it, is the change in distance or displacement with respect to time, delta d over delta t. Another thing that we've learned is that if you have a graph where you're graphing time on the x-axis and speed is graphed against that, or let's say v, well, the area under the curve is the distance. So let's say my speed is plotted out like this. If I could figure out a way to measure the shaded area here, well, that would be equal to the distance. Now, sometimes that's easy. Like, let's say we had a straight constant change in speed, triangle. We know that 1/2 the base times the height is the area of a triangle, so that gave us this equation. We found that distance for a constant change in speed that begins at 0 speed, it's just the maximum speed times the time change divided by 2. Beyond that, then we looked at acceleration, and we found out that acceleration is really just the slope of a graph that has speed versus time. So if you're plotting time here and not displacement, but rather speed, then the area under the curve is the distance, but the slope of the curve is the acceleration. So you could have a constant acceleration, or you could have changing acceleration where the slope would be equal to a at any tangent. In terms of an algebraic equation, acceleration is the change in speed or the change in velocity with respect to time. Now, we did a little more work with that, and we came up with two equations. There was a long, drawn-out derivation, but the bottom line turned out to be this. We had two very good equations that were very general for any starting speed, any ending speed, any time, any distance, that told us distance during an acceleration is equal to the initial velocity times the time that the acceleration took place over, plus half the acceleration times that time change squared. That was one of our important equations that we decided would be good to put in our toolbox. We also had another equation that gave us a final velocity, and that turned out to be final velocity is equal to the square root of the initial velocity squared plus 2 times the acceleration times the distance. And then we looked at a special case where a is equal to g, and both of these equations work, and that's when an object is just freely falling. Now we're moving on. Acceleration only happens when there's a net force on an object. This is called Newton's first law of motion, named after Isaac Newton, very famous, very powerful scientist from a few hundred years ago who first figured this out. You can't make a change in speed happen unless there's a net force on the object. Now here's what a net force means. We're going to talk about this a little bit more later on, but a net force means a force that isn't balanced on that object. So if I push hard in this direction on an object, but I push equally hard in this direction on an object, that's not a net force, and there will be no acceleration. If I push on this object very hard and I don't push at all from the other direction, or if I push only very lightly from the other direction, then I've got a net force. It's unbalanced, and so the thing will be accelerated. Another way of saying this is only force causes change in speed. Let's take a look at multiple graphs here and see what happens when we put force on an object. So we're looking at this object here, a ball or something like that, and on this graph we're measuring where is it, what is its displacement. Here we're measuring its velocity or speed. Here we're measuring the acceleration on the object, and here we're measuring the force. So we can get a relationship with the force that causes the acceleration, that causes the change in speed, that causes the thing to change its position. So let's take a look at several steps. First of all, I've applied a force. This arrow, this vector, represents a force pushing on the object. I have no displacement yet. I have no velocity yet. I have no acceleration yet, but I have seen my force jump up. Now, the force has been applied for a little while. Now, the acceleration begins to occur. As soon as I place a force on there, now I have acceleration. The force hasn't changed its size. It's still at the same magnitude here. That means the acceleration is constant. Force and acceleration turn out to be proportional to each other. If force doesn't change, acceleration won't. If I'm accelerating at any acceleration, well, that means that my speed is changing. That's what acceleration means. So I see an increase in my speed. Well, as my speed increased, another thing that happened is the object actually moved. And I saw it physically move here, and I saw a graph of motion. Well, the force is still constant after this unit of time, so the acceleration is still the same change. Acceleration being change in speed, well, I see my speed has gone up. Because my speed has gone up, this unit of time, the last unit of time, saw a bigger change in displacement than the first one did. Next unit, still constant force, which means still constant acceleration, which means still a constant change in speed. But the speed has been going up, which means in this next unit of time, I cover even more distance in my displacement. Same story here. Now the force suddenly drops to zero. When the force drops to nothing, I have no more acceleration. If I don't have acceleration anymore, my velocity isn't changing. My speed is the same. So that means I will now have a constant line that shows what my displacement is as long as there isn't any more change in speed. And that would require a force. Forces cause objects to accelerate, and they accelerate in this way. They accelerate in the direction of the force. So if I have a force that's pushing this way, my acceleration will also be that way. If I'm pushing straight east, I'll accelerate straight east. Now, acceleration doesn't always mean you're going faster. Acceleration may also mean that you're going slower. If the velocity was in the opposite direction of the force, if I'm moving west and I put a force on this way, if this is speed and this is force, I'm going to have an acceleration in this direction, and that'll actually slow things down. Sometimes we call that a deceleration. We also know that forces cause an object to accelerate with a magnitude that's proportional to the force. So the size of the force and the size of the acceleration are matched to each other. And then the third thing we know about forces and how they relate with acceleration is a force causes an object to accelerate with a magnitude that's inversely proportional, or kind of opposite to the object's mass. So a big mass will result in a small acceleration for the same force. Small mass, big acceleration. Well, this relationship that encompasses all these three things is called Newton's second law of motion. And in simple algebraic terms that actually turn out to be powerful problem-solving tools, we can say that force is directly proportional to the object's mass and acceleration multiplied together. So, bigger force, bigger acceleration if the mass is the same. Bigger force, bigger mass if the acceleration is the same. So F equals ma, Newton's second law of motion. Again, very important problem-solving tool. If you know acceleration, you can find force, or even mass. Well, this definition actually gives us a unit that we can use to describe force. If we think about the equation, F equals mass times acceleration. Let's plug in terms for mass. Mass is measured in the SI system in kilograms. Acceleration in the SI system would be measured in distance over time, that's a speed, over time. So that's an acceleration. Mass times acceleration. Well, this is the kilogram meter per second squared. It's a compound unit. Just to make notation simpler and to honor Isaac Newton, this quantity has been renamed the Newton. So 1 Newton of force is a kilogram of mass accelerated at a meter per second squared. That's how much force it takes to make that mass move forward at that increase of speed. This is actually a more useful unit, especially when you're getting started, because it encompasses all of the units that make it up. That's shorthand. Well, let's use F equals ma to solve a problem. This example says a force of 30 newtons is applied to an object that's at rest. So here's my object. I'm pushing on it with a force, and that force is 30 newtons. The object accelerates at 15 meters per second. So A is equal to 15 meters per square second, I should have said. Now, if F equals ma, well then m would have to be F over A if I do a little algebra on it. So my plan for solving this problem will be, I'm going to plug in my force, 30 newtons, but remember newtons are kilogram meters per second squared. That's F, but I'm supposed to divide by acceleration, which I'm told is 15 meters per second squared. Well, look what happens to the units. Meters drop out. I have seconds in the denominator, up and down, so they drop out, and mass comes out in kilograms. Well, that's a pretty good evaluation tool because that's the right unit for kilograms for mass. 30 divided by 15 is 2, so I could say that my mass must be about 2 kilograms. You can actually weigh things in a zero gravity zone by just accelerating them, and that's what they do, like in the space shuttle or places like that. Well, let's try another one. A force of 300 newtons is applied to a 30 kilogram object. So this is object, its mass is 30 kilograms. I'm pushing on it with a force that's equal to 300 newtons, which remember is 300 kilogram meters per second squared. Question is, what acceleration? So going back to Newton's second law as a problem solving tool, F equals ma, so that means A would have to be F over m. Well, my force was 300 newtons, or I'm going to write it fundamentally as kilogram meters per second squared. And then I'm going to divide by 30 kilograms. Well, the units, here's what goes on. Kilograms drop out. I'm left with meters per square second, and that's acceleration. 300 divided by 30 is just going to give me 30 divided by 3, which is just 10. So 10 meters per second is the acceleration on that object.